All right, in our previous video, we looked at the basic rules of differentiation, such as sum rule, difference rule, power rule, constant multiple rule, and we saw how to find the first derivative of just some starting off functions, some basic functions. And we also found that if you're given a function that may look a bit complicated, there's a good chance you may be able to rewrite the expression into a form where you can just simply use power rule. So if you don't know how to do product rule or quotient rule, you're not at a disadvantage. You can still find an answer to the problem. So in this video, we're going to continue that process looking at some other types of function setups and determine how we can find the first derivative without having to get into the product rule, the chain rule, the quotient rule, and still just use our basic rules to apply them and find f prime. So let's go ahead and get started with just a couple of problems selected from this section number 2. So we've already figured out how to handle problems like B here, where we have x plus 1 over x. We talked about in the previous video how we can simply rewrite this as x plus, and then we said that if we have something in the denominator, we're just going to make that exponent negative. So here we would have x to the negative 1 since it has a first power. So it's 1, negative tells us it's in the denominator. And we just take the derivative from there. So we just use power rule, not that big of a deal. Then we get into ones like C and D. And let's go ahead and let's go ahead and do C. So if we're looking at 2C here, we have x plus 1 over x. Now before you panic and think, oh goodness, I have to know how to do quotient rule, you do not. Dihydrogen monoxide. We're going to rewrite this so it's just as simple as water. So let's think about what we can do with a fraction like this. Well, if you think back to the days when you first learned about fractions, you learned that if you have multiple terms in your numerator and a single term in your denominator, you can just simply rewrite it to be multiple fractions. So here we have x plus 1 over x, which is just the same as x over x, so that denominator stays exactly the same, plus 1 over x. Because we have 1 over x over x, there they are. So if we keep going, x divided by x, well that's just simply 1. That's not too bad. And then this 1 divided by x is still 1 divided by x, but let's rewrite it knowing what we know now about our exponent rules. So we know that this is x essentially to the first power, and it's in the denominator of this fraction, so we can say it is x to the negative 1. So this is really what you're looking at, 1 plus x to the negative 1 when you see this x plus 1 over x. Slightly daunting or very daunting, not so bad. We can handle this. So let's take the first derivative of this and see what we get. Oops, not yet. This is our original function. So this is our original function f of x. Here we go. So when we take the first derivative, we're going to take the first derivative of 1. And the derivative of 1, it's just a constant number. So we'd say that it's 0, or you don't have to write it at all. I'll just write a 0 here so you can see it. And then for the second term, x to the negative 1, you would just use power rule. So negative 1 times essentially a positive 1 gives you a negative 1. So that's minus 1. Put our x here. Then we drop this exponent by 1, so negative 1 minus 1, which gives us negative 2. So then we would be able to say that once we're done, we have as our first derivative negative x to the negative second power, like that. Because essentially this 1, we don't have to write it, we can just simply write the negative and it's implied. If you wanted to take this and rewrite it back into a rational expression form, you'd have a negative, and you'd have that 1 to show back up again. You have a fraction. You have this fraction bar because of this negative exponent. It's telling me that the x squared is going to live in the denominator. So there it is, x squared. So either one of these, the negative x to the negative 2 or negative 1 over x squared, either one of them qualifies as your derivative for f of x. So that was 2c. Not so bad. The process that was most important to this was right here. I'm going to circle this in red. Was right here. The fact that we took what was one large fraction and divided it into two smaller fractions. And once we did that, we had individual terms that we could evaluate and find the derivatives of. So you'd want to think that through when you're doing something like part D, where you can just simply take that large fraction and divide it up into two fractions and go from there. Excellent. So how about we look at one like, ooh, E. That one looks like it's a bit much. So let's understand how we can handle E without doing product rule. And in fact, for E, I'm just going to set it up because you may already be thinking, wait, we just did some basic algebra to divvy up and find our fractions. Couldn't we just do some basic algebra to rewrite this into one long polynomial? You're correct. So with this x plus 1 and x minus 2 from 2e, don't think product rule, because technically we haven't covered product rule yet. Think FOIL. So first, outer, inner, last. Remember that goodie? So let's go ahead and do that. So multiply your first terms. You have x squared. Multiply your outer terms. So x and negative 2. So negative 2x. Multiply your inner terms, so positive 1x, so it's plus x. And then your last terms, positive 1, negative 2, minus 2. So if we clean that up and combine like terms, we get x squared minus x minus 2. Again, dihydrogen monoxide, it's just water. It's just simply x squared minus x minus 2. This we could take the derivative of and not even worry about it. It's easy enough. Okay, so I'm just going to leave this one for you to do because now you can see I just have to simply take the first derivative of x squared minus x minus 2. We can do that in our sleep. Not a worry there. So how about when we get to f? This one's a little bit different. We know how to handle this first term. We've already figured out how to deal with exponents and how to rewrite those. But then what do you do with the square root? That one's a bit new. So let's talk about how we can rewrite square roots. And in fact, it's just more dihydrogen monoxide. It's more just taking what you see and rewriting it into an exponent form. So let's continue on with that. So with f we have, here's my f of x, we have 1 over x squared plus 6 times the square root of x. So here's another useful exponent fact for you. When you have any type of root, whether it's a square root, a cube root, a fourth root, whatever it is, you can take that root and turn its exponent into a fraction because that's really what it's saying. So for here, I'm going to write this in green off to the side so you can see it. When you see square root of x, it's like you have a 2 here, right? Because it's squared, so it's the idea of power of 2. So that means that you would say it's x to the 1/2. And that is what it looks like in exponent form. So the idea is that if it's a square, there's a 2 here, you're putting a 2 in the denominator of your exponent x to the 1/2. And just to continue it on in case it shows up later on, what if you had a cube root? Same type of rules apply. You'd have x, which is just simply what's here in your radical, and you would say instead of x to the 1/2, which is for square root, you'd say x to the 1/3. Because it's a cube root. So whatever number you have out here for your root, that's what you're placing in the denominator of a fraction exponent. Kind of useful, huh? So let's apply that then to 2f. So we know that this first part, 1 over x squared, child's play. We know that the denominator, or this x squared in the denominator, is just simply telling us that we have x, and there's a 2, and it's in the denominator, so it's a negative exponent, and we're done. Then we have, this plus 6 times the square root of x. So we'd say plus 6 times, and the square root of x we said is just the same as x to the 1/2. So it's just x to the 1/2. And from here, we can use power rule to be able to figure out our first derivative. So let me get some more space here. Here we go. And we'll take our first derivative. So we have f prime of x. And we just go through and we use power rule. Just that simple. So we have x to the -2. So that means we're going to take this -2, multiply it or move it to the front, if you will, to this 1. So -2 times 1 gives us a -2. Then we have x to the, take that exponent, drop it by 1. -2 minus 1 gives us -3. So that's the first term down. Let's handle the second term. So we have 6x to the 1/2. Still using power rule. Rules are still the same. So I take 1/2, I multiply that with my positive 6, and that gives me a plus or positive 3. There's my x. And then for this 1/2, I'm dropping it by 1. So that means I'm thinking 1/2 minus 1. So 1/2 minus 1, I'm short. I'm going to need an extra 1/2, so I'm going to have -1/2, and that becomes our exponent. So it's x to the -1/2. And this is our first derivative for 2f. Excellent. So that's how you would handle any type of square root that comes up. Just simply rewrite it into this exponent form and just go from there. So when you see something like, for example, g here, mark it with a little blue. Here we go. When you see something like g, you actually have two of the rules we talked about applying. You have a function, or an expression rather, in your denominator, and that expression has a radical to it, has a root to it. So you'd use the fact that it's in the denominator, which tells you it's a negative exponent, and then you have that it's a square root, which tells you, as we said here in green, 1/2. So you could rewrite for g this as x to the negative exponent because it's in the denominator, 1/2 because it's a square root, and you're taking the derivative of x to the -1/2. Easy as pie. So when you look, continuing on this discussion, and you look at h and I, it's similar to what we were doing in E. So just in case you were thinking, okay, we've handled roots, we're good with what happens with foiling, but how do I handle ones like h and I? For h and I, just take them and break them up into their individual parentheses and just FOIL them out. So for example, with h, you have 2x minus 1. I'll do this one in purple. There we go. So you have 2x minus 1 squared. Don't worry about chain rule. We'll be fine. We can think about this as 2x minus 1 times 2x minus 1. We'll FOIL that out, and whatever you get, take the derivative of that, and you're on your way in terms of finding your derivative. Just that simple. And you can use, likewise, a similar strategy here for x plus 2 cubed. Remember, this exponent just simply tells you, when it's an integer, how many times you're multiplying this, this set of parentheses to itself. So in this case, it's x plus 2 multiplied to itself 3 times. So it's x plus 2 plus x plus 2 times x plus 2. And I would recommend to just do FOIL with 2 parentheses at a time. Work that out, and then do your foiling method again with the your new parentheses and this third one. And just simply go from there. So like I said, with a lot of these problems in terms of just applying our basic differentiation rules, it's a lot of dihydrogen monoxide. It looks really complicated, but then once you realize, oh wait, it's just simply water, it's not so bad. So be sure to review this video again and to write down these items in green with talking about the roots. And of course with the previous video, noting that any type of denominator or anything that's hiding in your denominator can just be written as a negative exponent. And that should help you quite substantially in solving some of your basic differentiation problems. Hope this helped.